All right, here's an example where we're going to find all the zeros of a polynomial function. We're going to first use the rational zero theorem to find the possible rational roots. So we're going to take the factors of c over the factors of the leading coefficient. So that will be plus or minus 8, plus or minus 4, plus or minus 2, plus or minus 1 over plus or minus 1. So the possible choices could be plus or minus 8, plus or minus 4, plus or minus 2, or plus or minus 1. So that gives us 8 possible choices. Now if we use Descartes' rule of signs, we could see how many possible positives there might be. So we're going to start with the original function and watch the sign changes. So we have a positive, a negative, a positive, a positive, and a positive. So we have 2 sign changes. So that means we have 2 or go down by an even amount, so 2 minus 2 or 0 possible positive zeros. For the negative zeros, we need to evaluate the original function for negative x. And then simplify it. And then look at the sign changes. Positive, 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 negative, positive. So there are 2 sign changes, so we go down by an even amount. So there are 2 or 0 possible negative roots. So we don't really have a narrowing down in that respect. What you could do next is you can now start by graphing the function with your graphing calculator to help find that first 0 or root. So go ahead and type this into your graphing calculator or the Desmos app. And here would be your x and y axes. And when you graph that out, you're going to get a possible x-intercept, looks like right here at negative 1. So we're going to check using synthetic division if that x equals negative 1 is a 0 of the function. So we have it set up now. Bring down the 1, multiply it, add it, multiply it, add it, multiply it, add it, multiply it, add it. That remainder is 0. So yes, this is a 0 of the function. In factored form, it looks like this. And this is your x-intercept, negative 1, 0. So then you would factor x plus 1, and now what's left is a new polynomial where you drop the degree, so you're going to go down to an x cubed, x squared, x, and constant. Then you would try and factor this to find the other three roots, or continue with synthetic division. Now, I want to remind you about repeated zeros. When they have an even multiplicity, at that x-intercept, it bounces and turns around. So that's telling me that at that intercept, that multiplicity is even. So I have another root there. So I'm going to continue factoring, and I'm going to take out another x plus 1, or another repeated 0 out of that green. So now I'm going to work with the green cubic function. I'm going to do synthetic division again. And I'm factoring out x equals -1. Coefficients. Here we go. Bring down the 1. Multiply. Add. Multiply. Add. Multiply. Add. We get another 0 because that remainder is 0 when we synthetically divide. So what's left is a quadratic function. So I have the function now as f of x equals x plus 1, which was the first factor. Then we took out another factor of x plus 1 in the green. And now what's left is a quadratic. And now we can either factor this or use the quadratic formula if it's not factorable. So are there factors of 8 that add to -4? To think about factoring 8, you could do 4 times 2, -4 times +2. So those are not factorable, so we'd have to then use the quadratic formula. Simplify. -4 is +4. Underneath the radical, 16. -4 times 1 times 8 is -32. Divided by 2. Continue simplifying. Underneath the radical, so you're going to get -16 divided by 2. Uh-oh, we have a negative square root, so that's a imaginary number, complex number. So we're going to put that as an I, square roots of 16. Then the square root of 16 is 4. Then separate out the fraction into 2 fractions. Reduce those fractions by 2 by a common factor. And these are your last 2 zeros. They are imaginary or complex zeros. And if you remember, complex zeros occur in pairs. So these will not be x-intercepts. They're just going to be zeros of the function, imaginary zeros.